I'll talk about joint work with Andrea Pasquali and Diego Velasco on orbifold diagrams and associated algebras and categories. Let me explain first what an orbifold diagram is. So we always work with a disk with n0 marked points on the boundary. And I call that sigma n0. Then we have an orbifold point omega of order d larger than 1. And then we also have a permutation tau in the symmetric group on the n0 vertices. Then an orbifold diagram omega O is given by n0 oriented curves in that disk, gamma 1 up to gamma n0, which go from I to tau of I. So permute the vertices. They should have transversal crossings, and crossings should alternate. So whenever I follow a strand, the other strands I will meet will come from the left and the right, and that will alternate. I have only finitely many crossings. Then there is a condition which I circled as orange, that we can have two strands meet in parallel, and go in the same direction and then meet again. Well, we only allow that if the omega is inside this disk that they form or region, and the strand may also self-cross itself, but then again I want to have omega inside. There is also a further condition which I will just illustrate briefly. D should be larger than, D hasn't been mentioned before, should be larger than winding numbers in self-crossings. So whenever I have a self-crossing, I look at subcurves given by the cross self-intersections and count the winding around omega and look at the values. Or whenever I have two strands meeting in parallel, I also look at the loop they form, like going along gamma 1 and backwards gamma 2, and take the absolute value of these winding numbers. So these should be larger than that. I've drawn two examples here. One A has n0 equals 3, d equals 3, and tau is the identity in S3, and the other one has only 2 marked points on the boundary. The degree is 5, and again we have the identity. Okay, you have this also on the poster, so you can have a look later if that was a bit quick. For motivation, well, these diagrams really are inspired by Posnikov diagrams or alternating strand diagrams, which have sort of the same conditions except for the last two. So this extra condition star orange is omitted, which means no such things and no self-crossings are allowed. Yeah. Well, I should really do it like that. Then the last condition is chosen in a way so that if I take such an orbifold diagram and I take its default cover, call this result symmetrized version of O or P, this is a Posnikov diagram. So it means that these forbidden sub pictures will vanish. It's d-symmetric for a disk with n0 times d vertices. Now, if I start with such a symmetric, the rotational symmetric Posnikov diagram, I can also go back and take the d-fold quotient. And this works nicely if you assume that d is at least 3. Okay, so these are the orbifold diagrams. I use them to get to algebras. The idea is that I start with an orbifold diagram, I associate the quiver to it, and also relations in terms like given by potential from the orbifold diagram. The algebras are going to be called AO and BO. So AO is just given by this quiver with the relations, and BO is an idempotent subalgebra of AO with respect to boundary vertices. So let me explain what the quiver is. I've redrawn the two examples, and I'll do this on the first one. These strands divide the disk into oriented regions, which means all the segments around it form an oriented cycle, and alternating regions. And in the quiver, I want for each alternating region, I want a vertex. Yeah, I've done this in black. Also outside of the disk again, just drawn the quiver again. So I get 3 outside, 3 more to the middle, and 1 in the middle. There will be arrows given by the strands. So you see here the red strand and the green strand tell me I should point an arrow from outside towards the nearest vertex inside, and similarly here I go outside. Okay, well, I've done this more carefully in the little picture below. And then if you look at the quiver, it also comes with regions. First of all, I should point out an extra rule. So this center region is alternating, and then in that case our quiver will have D vertices for that central region. So I've drawn them here, 3 vertices just next to each other, and each comes with arrows from the neighboring regions. So we have 3 paths, like sort of in parallel. And this is an extra rule. It doesn't happen when the alternating region is oriented, like in the other example. Now I should say how this potential is defined. Inside the quiver, I've drawn clockwise regions and anti-clockwise regions. I call them C1, C2 up to C4. And then the clockwise and anti-clockwise regions around this special vertices in the middle, they come like in 3 pairs. So it's not a planar graph anymore. It should look like you have 3 disks glued to each other along this middle 3 cycle. And the potential is going to be the positive terms C1, C3 minus C2, C4. And then for the middle region we have C11, C21, C31. And subtract xi times C12, C22, C32, where xi is a primitive root of the identity. Okay? So that's one way, and then the other situation is when the middle region is oriented, then we get a cycle around it. Here is just a loop. Again, the potential has as terms negative C1, because C1 now was clockwise, plus C2 minus C3 plus C4. And then the special thing is around the central oriented cycle. We take that to the power of D and 1 over D. Okay, so that gives me like an element in the path algebra, really. The relations it defines can be viewed on the quiver, like whenever I have an internal arrow far away from the center, it means that if we go backwards one way, it should be the same as backwards the other way. So that's, and then it's slightly different around the central region. Okay, well, that means we can associate algebras to these Orbifold diagrams. Now I also want to find categories or modules for these algebras, but really they are for algebras given as quotients of pre-projective algebras. For that, I've drawn here an affine type A quiver with doubled arrows, and I will define BKN. So now K is between 1 and n as the path algebra of this quiver modulo the relations xy minus yx. So at every vertex, I will assume that this is the same as that. And that's pre-projective algebra type relations, and then also x to the k minus y to the n minus k. And this was defined by Jensen, King and Su in the work on the corresponding cluster category. Now for the Orbifold diagram I need a slightly modified version. So now let's assume that n is a multiple of n0. Then I take the pre-projective algebra underlying quiver as gamma n0. Again, I want to have xy is the same as yx for all these vertices n0. Now the other relations will involve longer paths, so I really take again y to the n, which was a multiple of n0. So I go around more than once. Okay, so for B, the center of this algebra is very nicely described because we can just use T, which is the sum of all the xi, yi, and it's the completely polynomial ring in that. So that's the center. And I should say we take completed versions everywhere. Okay. Then Jensen, King and Su defined this category Fkn as Cohen-Macaulay module over the algebra Bkn. In that case, they are the Bkn modules which are free over the center. And that is the corresponding cluster category. Okay. I will briefly explain how we can think of modules in that category. So what Jensen, King and Su show is that certain modules come in bijection with k subsets of 1 up to n. And let's do it on an example. I take n equals 9 and I is 1, 4, 5. So these modules are free over the center, and I take the smallest possible modules which have at each vertex just one copy of the center. And then I should say how these copies of the centers are linked. So I should really say, like if we look at the copy of the center here, how the constant factor is linked across the xi's and yi's. And for 1, 4, 5, I want that x1 keeps constant factor, x4 like keeps the degree, x4 and x5, and then the y's, which are complementary to it, also keep in the degree. And if I have like x2, it will send me from a 1 to a t. So this should be viewed as a lattice diagram on a cylinder which is infinitely high. It just goes on forever because also you've seen the algebra goes on forever. Okay? These are rank 1 modules because when we restrict to a copy, like to the center, and just look at one of these vertices, 1 up to n, we really have one copy of the center. Okay? Now I want to have modules for our new algebras, and in one way we can just use the picture from above, but wrap it around more tightly around the cylinder. And what does it mean? Well, we have chosen n0 to be a factor of n, because we started with a default orbifold point, and with the orbifold diagram we went to n equals d times n0. So we can keep with our example, and n0 is 3. So instead of going around the whole cylinder, we want to stop, say 1, 2, 3 after 3 steps, and then again 1, 2, 3 and 1, 2, 3, and wrap this around tightly. So this gives a little bit of a mess, but I've tried to draw it using colors. So let's start. Like if we look at, again we take the k subset 1, 4, 5 to use the picture above. When L is 0, so we divide 1 to 9 in 3 parts according to D. 1, 2, 3, then 4, 5, 6 are 1 plus 3, 2 plus 3, 3 plus 3, and then the last 3 bits. So in L equals 0, we have an X. This is purple. Then we have 2 Y's. Now we have to wrap around already. We keep the level. We get here, and L equals 1 So that corresponds to x4 goes down, x5 goes down, and then we have a y6 going up. Then we keep the level and we have all y's going up all the way. And you see, I've tried to indicate that the module goes down here. So of course it is also infinite, that lattice picture. So you take again n copies of this CT with layers given by this L equals 0 up to d minus 1. And I call this module Li n0, which is equivalence up to class up to adding n0. Well, it does depend on choosing a representative, but then we can show that Li n0 is isomorphic to Lj n0, even only if I and j are in the same class. So this gives us modules for this algebra. And how can we link now the algebra and the orbifold? For that we should restrict to the case where we have an orbifold diagram which comes with tau equals identity, and where the symmetrized version has permutation I goes to I plus k. Again, k is smaller than n. We associate to that a module for bkn n0 by picking these modules we just constructed for the regions, for all the alternating regions in the orbifold diagram. There is like a unique way you can define labels for this orbifold diagram, and so each orbifold diagram gives us such a module. And then what we can show is that BO is isomorphic to the algebra B and 0k n up, or if we look at AO, it is really the endomorphism algebra of that object TO. This is in the same way as our result with King and Marsh, where we worked in the Grassmannian cluster category setup and the Postnikov diagram with this special permutation. Yeah. Just a final remark, if we consider this Q-group category of Fkn for the cyclic group of order D, this is a nice category and it does contain the module TO, but we don't really have a way to describe it. So we don't know yet whether we can also use a nice characterization as subcategories of modules, of the category of modules for this algebra B and 0kn. Thank you.